Let's talk about now nucleophilic aromatic substitution, which I will abbreviate NAS, although occasionally you'll see it as a substitution reaction of an aromatic. So you'll see it sometimes as SNAR, but I typically will call it NAS. So nucleophilic aromatic substitution. In contrast with our previous aromatic substitution, which is electrophilic, benzene was the nucleophile and it attacked an electrophile. However, in this case now, benzene is going to be our electrophile and it will be attacked by a nucleophile. And this reaction is actually a bit simpler than electrophilic aromatic substitution is. So, in this reaction, we're going to see that we need a couple of things. We need, first off, a leaving group to be present. Typically, this is a halide, although you may see other types of leaving groups as well. So you'll need a leaving group. You'll also need a strong electron withdrawing group, ortho or para to the leaving group. And then third thing, of course, you're going to need a strong nucleophile. And as we remember, strong nucleophiles are those that have localized negative charges. Things like hydroxide, cyanide, those ideas. The ones that are not stabilized. So OH minus or CN minus. Either of these are good, strong nucleophiles. Those are just examples, right? And in this reaction, we're going to see that we will essentially be substituting our leaving group. So if we were to take this para-chloro-nitrobenzene and react it with, say, NaOH, heat, and then step 2, you have to do an acid wash, by the way, for this. If we were to do this, I know we're going down this time instead of to the side, but that's okay. What ends up happening is you'll end up kicking out your leaving group, and everything else stays the same. And so we'll take a look at the mechanism for this. And just to specify, very often your strong EWG, there's really two options that are generally seen here. We see that the nitro group is the preferred strong electron withdrawing group, although a sulfonic acid works as well. So you really need these two because you need the resonance that's going to happen here. So let's take a look at the mechanism. When we treat this para-chloro-nitrobenzene, I'm going to actually go ahead and draw out my nitro group. You'll see this is going to be the same for a sulfonic acid. The idea here is that we need it to be able to resonate. And let's have a look why. So here comes our dear friend, the hydroxide. So hydroxide, good nucleophile. We have everything all set for our NAS reaction. We have our para-situated chlorine. We've got our nitro group ready to go. And your professor has forgotten his formal charges. There we go. So let's take a look at how this mechanism works. So our nucleophile will attack the site upon which your leaving group is situated. And the reason that our EWG needs to be ortho or para is because the resonance that's going to come out of this is necessary to be soaked. So as we resonate through, we see that the nitro group is exceptional because it can actually go ahead and carry that negative charge that's going to come out of this all the way to the oxygen, which is the best place it can be, right? As we do this, we see that we'll end up with the following. So we have an OH and we have a Cl. And we have our nitro group, which is now double bonded. And we've got the two negative oxygens. This is the most stable resonance form, although there are others. And what's going to happen now as this closes down, just like before, we're going to restore our aromaticity by kicking out our leaving group. So The electrons are going to come down off the oxygen, they're going to go back into the benzene, and they're going to kick out your leaving group, thereby giving us our product. And so we see here that we're going to end up with OH here. We have our 3, and then we have, again, our nitro group. Technically speaking, remember that phenol is pretty acidic, and if you have extra base hanging around, it's going to deprotonate that phenol. Remember, phenol has a pKa of about 10, whereas hydroxide's got a pKb of like 0. So it's going to go ahead and grab that proton. You're going to technically get a phenoxide. So you just need some acid around to reprotonate that. So that's why you need an acid wash if you're using hydroxide. If you're using a nucleophile like cyanide, the water wash is not necessary. In fact, water will ruin your cyanide, as we'll see in when we talk about hydrolysis of nitriles later on. So, within this, there are a few important considerations about resonance that we have as well. And so while I've drawn the arrows going towards the electron sink, which is going to lead us to the most stable resonance form, in theory, adding a nucleophile to the benzene does create a negative charge which we could delocalize. And so we have what's called a Meisenheimer complex. So if we have, say, an electron withdrawing group, we've got our leaving group and our nucleophile here. Well, let's do it without the nucleophile first. So I'm just going to have it para just because I feel like it, but it could be ortho as well. Just remember, for meta, though, it doesn't happen. If your leaving group is meta to your electron withdrawing group, this reaction does not occur. So just keep that in mind. So here comes our dear friend, the nucleophile. Remember, we want a strong nucleophile, so it should be negatively charged. We have options here. Oops. That comes in. And let's just, instead of resonating, let's just put this negative charge onto that first carbon. And since I'm out of space, I'm going to scroll down just a little bit here, just so we can see all the different resonance that's going to be taking place. So we have our leaving group, we have our nucleophile, we have our electron withdrawing group. And now we have a negative charge here on the benzene. And just like before, technically speaking, notice, by the way, that the negative charge is now on an ortho position, so having an electron withdrawing group on that ortho position is a good idea, right? That's going to help stabilize it. If it's a ketone, it can resonate to it. If it's a sulfonic acid, it can resonate into the sulfonic acid. So, but we can just resonate it throughout the ring if we are so inclined. We could go right next to the electron withdrawing group. That's probably pretty stable too. Like if you have a trihalogenated methyl group, putting a lone pair nearby is not the worst idea. Although, again, typically NAS is done with nitro compounds and to a lesser extent sulfonic acids. So if we do this resonance, we will now move our negative charge down to our electron withdrawing group. So it's going to withdraw those electrons and help stabilize that molecule. And if we to resonate again, we could resonate it back onto the other ortho position. Or again, if our electron withdrawing group is an electron sink, meaning it's got resonance like a ketone, like a nitro group, it could resonate there as well. So, and notice now we're on that other ortho position. So in either case, ortho or para substituted electron withdrawing groups will work. Because we see here that electron density is localized to the ortho and para positions. So we're going to want electron withdrawing groups there to stabilize that negative charge. This all is called a Meisenheimer complex. And it is essentially the same thing as a sigma complex, except it's a negative charge now. And whereas a sigma complex was stabilized by an electron donating group, a Meisenheimer complex, which is a negative version of it, is stabilized by an electron withdrawing group. And so for this reaction, you just need three characteristics. You need a leaving group that is ortho or para to your electron withdrawing group. If you have multiple, that's fine. Multiple electron withdrawing groups, that's great. You need a strong electron withdrawing group, at least one, using nitro or sulfonic acid, lesser extent ketones even, or other electro resonatable groups. And then you also need a strong nucleophile. So something like hydroxide, like cyanide, something methoxide, a sulfoxide, not a sulfoxide, a sulfide. Sorry. Something like that. Strong, localized negative charge ready to attack something. All right. And so, with this reaction again, your nucleophile just will displace its leaving group, and you can get this reaction to happen if those three criteria are met.